This video examines the tuning of the scrubber duct inlet temperature controller. Previous videos examined the hot air pressure, the hot air temperature, and the baghouse inlet temperature controllers. Our starting point is all previously tuned controllers on auto. Display the tuning parameters for the scrubber duct inlet temperature controller. The controller gain is 10% to percent. The reset time is 1.5 minutes. In a temperature loop, a controller gain of 10 is not a concern. The scrubber duct inlet temperature loop involves the mixing of two streams and should respond rapidly. One would expect a shorter reset time. Switch the temperature controller to auto. Then change the set point from 80 to 85 degrees Celsius. The scrubber duct inlet temperature is assigned to the cyan pin. The response exhibits a hump that is similar to the one exhibited by the baghouse inlet temperature loop. Place the simulator on hold. The reasons for the hump are largely the same. When the controller opens the hot air damper to scrubber duct inlet, the additional hot air causes the temperature to increase rapidly. This also causes the hot air temperature, the red pin, to decrease significantly. Because of this, the rapid initial increase in the scrubber duct inlet temperature is not sustained, hence the hump in the response. To reflect the dynamics of a mixing process, the tuning should be a shorter reset time and possibly a higher controller gain. Increase the controller gain to 20. Place the simulator on run, and change the set point from 85 to 80. Initially, the scrubber duct inlet temperature responds more rapidly. However, significant oscillations are now present, especially in the hot air temperature, the red pin. These oscillations decay too slowly to be acceptable. We must return the controller gain to 10. Shorten the reset time from 1.5 to 0.75 minutes. Then change the set point to 85 degrees Celsius. Shortening the reset time provides a much slower response in terms of the period of the oscillation. However, it also exhibits an increased oscillatory nature. Shortening the reset time has not improved the response. Place the simulator on hold. The initial drop in the hot air temperature, the red pin, is almost 30 degrees Celsius. This loop is being upset by the control actions of the baghouse inlet temperature controller and the scrubber duct inlet temperature controller. The hot air temperature loop responds more slowly, so the impact of these disturbances on the hot air temperature is significant. The scrubber duct inlet temperature loop is not performing satisfactorily. and repeated efforts to tune the loop are unlikely to be successful. The analysis of a loop with performance issues often begins with an assessment of the cause and effect relationships. Consider an increase in the set point of the scrubber duct inlet temperature controller. The following ensue. For an increase in its set point, the scrubber duct inlet temperature controller opens the hot air damper to scrubber duct inlet. This steals some hot air from the baghouse inlet, causing the baghouse inlet temperature to drop. The baghouse inlet temperature controller opens the hot air damper to baghouse inlet. Opening the two hot air dampers drops the hot air pressure. The hot air pressure controller opens the fresh air damper. The additional fresh air causes the hot air temperature to drop. The hot air temperature controller opens the fuel gas valve to increase the heat input to the furnace. All of this seems logical, leading to the conclusion that the scrubber duct inlet temperature controller should function properly. But this ignores a couple of issues. Actions taken by the scrubber duct inlet temperature controller upset the other three loops. The hot air pressure loop and the baghouse inlet temperature loop are fast, so these upsets have only a nominal effect. However, the hot air temperature loop is slow, so these upsets have a major impact. The cause and effect analysis ignores dynamics. The issues pertaining to dynamics are similar to those for a cascade configuration. For a cascade to function, the inner loop must be dynamically faster than the outer loop, preferably by a factor of 5. In a cascade, the outer loop is totally dependent on the inner loop. Switch the inner loop to manual, and the outer loop cannot function. A similar dependency exists in the single loop configuration for the off-gas process. Increasing the scrubber duct inlet temperature while maintaining all other variables at their targets requires an increase in the firing rate to the furnace. The hot air temperature controller determines the fuel gas valve opening and consequently the firing rate to the furnace. This makes the scrubber duct inlet temperature controller totally dependent on the hot air temperature controller in order to function. Switch the hot air temperature controller to manual, and the scrubber duct inlet temperature controller cannot function. The relationship between these two loops is not a cascade configuration, at least by the commonly accepted definition of cascade. But the requirements stated for cascade apply to any configuration in which one loop is totally dependent on another loop. If a slow loop depends on a fast loop, the configuration will function. But if a fast loop depends on a slow loop, performance issues will arise. The scrubber duct inlet temperature loop is a fast loop that is dependent on the slower hot air temperature loop. The result is the hump exhibited in the responses for the baghouse inlet temperature and the scrubber duct inlet temperature. And like cascade, repeated attempts to tune such loops prove futile. The next video considers the options to obtain a control configuration that delivers the required performance.